I'll be talking about using computational chemistries to screen the UV-Vis spectra of our metal cation complexes with our crown ethers. So, but why would we want to do this? Since it's easier to just take a solution of our thing, swish it, da-da-da, and then run and get our spectrum out on the computer, right? But there's this additional time that we need to take to actually synthesize our compounds, make the solutions, and then prep everything and getting it all ready to go, which will take forever, and you can only do them one at a time. So, why not do them all at once? Which is why we want to do this. And what I will be showing you is the result of about 1.5 evenings worth of computations. So our first up is our crown ether, the base molecule that I synthesized this morning that I talked about, is this guy. And I ran it through both Gaussian and VASP, just because we can. And we see our UV-Vis from Gaussian and VASP and the density of states, because it looks cool, and I thought it would be fun. So if you look carefully at the wavelengths between the two predicted spectra, they don't exactly agree, but that's okay, because what we're looking for is a change in the UV-Vis upon complexation with our metal cations, which we will see, I promise. Note 500 nanometers and about 250. So when we complex this guy with potassium, that huge peak that was at 500, gone. It's done. Instead we have this peak in the red minus 700. And in the Gaussians, it's shifted a little bit in the same direction. And so the change between the two are the same. They're showing the same change, which is what we're looking for, which is awesome. And then again with calcium, it's totally different. With just one peak, we have this, and then Humpy-Doo, and then all those things. So this should provide some interesting binding character when we actually look at it. And then similarly, in the Gaussians, it's shifted down by 50 nanometers. But why do one branch of molecules when we can do all of them? So here's the Sapp with the phenylhydrazine that we added also earlier this morning into DOS, because that also looks cool. Now this spectrum is a little funkier than just our plain crown ether, but it's also cool, with a peak between 400 and 500 and right around like 630 shown in there. One of which correlates to, in the Gaussians, right over here. And then this little bitty boo at just above 500. When we complex that with potassium, magic happens, right? We get this change, and we get 0 here, almost 0. This pretty much stays the same, and this just skyrockets. And then instead of 2 peaks, we see one big broad peak from the Gaussians. So again, what they're saying is, yes, the UV-Vis will change. There is some energy level shuffling going on. And for calciums, what we see again, we see the growth of these peaks here, and then just an absolute absence of absorbance between 5 and 600. And then over in the Gaussians, we see this big, huge old peak near 400, just above 400, and then that trailing tail off into 2000, which is again what we're looking for. They're showing that the UV-Vis will change on complexation. So, in short, built a bunch of ligands, stuck metal cations in them, ran them simultaneously, all at once, over the course of one night. Actually, making the PowerPoint took longer than running the calculations, setting them up and going. So that ought to tell you something. And so even though the resultant spectra may not agree between the Gaussian and VASP softwares, they both show that there will be similar absorbance changes in the UV. Then that's logistics. Any questions?
Okay, let's thank Paul.